So I will now share my screen and we will be talking about the intro to integral calculus. Can you see my screen, class? We're on module 1, integration concepts and formulas. Can you see my screen?
Yes, Miss.
Okay, thank you. Okay, so we will proceed with what you have on your screen. And this is the introductory part of your course on integral calculus. It's very fundamental in nature, but we will start with this first. So for this afternoon, you will be introduced into integration concepts and formulas. After this module, you will be introduced to techniques, how to use these formulas or added techniques other than these formulas in handling and evaluating integrals. So before we go to our main course, if this is incomparable to the meal, we'll first look into the things that you have learned last semester, and it's very important that you are able to differentiate. Can you get a piece of paper there, a ball pen, and find the derivative, and that is the second derivative of 3x cubed plus 2 over x. You may place your answer in the chat box. The second derivative of 3x cubed plus 2 over x. Okay, we have an answer already. So the answer here given by Beatrice is D. Okay, what about the rest? What's the derivative? The second derivative of 3x cubed plus 2 over x. Okay, let me ask. Okay. What about Cassie, John? What's your answer, Cassie or Casey?
4 over x cubed plus 6, miss.
What letter is that?
I can't, miss, see the screen. Alam ko na yung snap ng screen sa may integration concept and formulas.
What's the letter? What's the answer?
Hindi ko pakita sa choices, miss.
You cannot see the choices.
Oo.
Why? Why?
Lang ko na yung Japan sa may intro, sa may EMA 102 module 1.
Okay.
Ang screen.
Wait, huh? You cannot see, class. You can't see the slide.
Wala, miss, naka-presentation mode daw, naka-view tanan sa kilid.
Excuse, ha? Excuse. Let me, thank you, wait. So you cannot, ari di siya sa kilid, amuning makita niyo. Why siya ga presentation mode?
Yes, miss.
Let's see. I'll try again, ha? What's happening to this? Is it on presentation mode? Not still on presentation mode?
Wala Japon, miss.
Oh, so you see already the answer if that is the case. Anyways, I don't know what's wrong with my laptop. It cannot do projection. Wait ha. Let me stop sharing ka na classmate la ha. Wait. Anyways, so If you can still see this one on presentation mode, then you will be seeing already the answer anyway. Can you see it in presentation mode? No?
No, Miss.
Okay, so there's no point in asking a question because you can see anyhow the answers if it's still on this particular. Okay, I'll check class ha kung mag-change ko. Is it on presentation mode?
No.
Okay. Okay, so if you do your review of differential calculus, if you find the second derivative of the function of x that is given here, the first thing that you will do is, of course, not ask you anymore because you could see the answers already. So you find the first derivative, and that would be 9x squared minus x, or that would be minus 2x raised to negative 2. That happened because this x is raised to negative 1. And if you have it differentiated, that would be 2 times negative 1 times x raised to negative 1 minus 1. So you have it as x raised to negative 2. If you get the second derivative, that would be 18x, and you will have plus 4. This would be positive already, x raised to negative 3. So your answer is D for that one. Now, whereas for this one, for number 2, if you will find the derivative of y equal to 3 square root of x minus 5, closed quantity raised to 8, this will require you to do chain rule. So what's the chain rule of differentiation? So the first thing that you will do is perform the differentiation based on the power or exponent in which this entire u is raised into. So you use power rule. So your dy dx, the derivative of y with respect to x, is equal to, using power rule for this, followed by the application of the chain rule, you will have 8 times 3 square root of x minus 5. That would be raised to 7. But that doesn't stop there because we need to get the derivative of this. So we multiply, I'll place it here below, 3 by 1/2 x raised to negative 1/2. Because this x is raised to 1/2. And if you will subtract 1 from that, that would be x raised to negative 1/2. So if you will simplify, you will have here 24, 8 times 3, 24 divided by 2, that would be 12. And you will have this quantity 3 square root of x minus 5. We raise that to 7. And this x raised to negative 1/2, or that's 1 over the square root of x. So the answer that you are seeing is letter D. So that's a review on what you've learned last semester. If you will continue with some more functions to be differentiated, you will have the second of x squared. So since your variable here is, this is probably f of x plus. So the f was missed to be written there. It was not written. So you have the function of x prime. So that would be the derivative of this expression. We'll have 1/2 for this square root times the second of x squared. So this would be now negative 1/2. And the derivative of the second is second x squared tangent of x squared. And then the derivative of x squared, which is 2x. Now these 2 and these 2 will cancel each other, leaving you with, so you have x. So you have x, then you have this square root of x squared. This is square root plus in the denominator, like this one. And you have this one, which is raised to 1. So then you will have the square root of second x squared. You get it? Because this is understood to be raised to 1 minus 1/2, so you still have 1/2. Tangent of x squared. So the answer is this one. Okay? You simplified by combining these two second functions here. Okay, somebody wrote in the chat box. It's okay. It's noted, Marion. Thank you. Anyway, this is recorded. So you have this as the answer. Now, for number 4, if you get the derivative of the log, so function of x prime. So what's the derivative of the log? Okay, what's the derivative of the log? You get first the derivative of this one. So that would be 3x squared minus 2. And then ln of this base of the log. Based on the formula, if this is your u, ln of, or rather ln. If this is your u, the derivative of the u multiplied to the ln of the base of the log, that's base 4, divided by the u. So your u is this x cubed minus 2x. Based on the formula that you've learned last semester. Derivative of the log is du over u times the ln of the base of that particular log. So this is 4. So you have ln 4. Okay, this is just but a short review on the main objective of differential calculus, and that is on differentiation. So before you continue your journey in calculus, and that is for integral calculus this semester, make sure that you review what you've learned last semester regarding differentiation. Okay, so now we will proceed to the next part of the slide. There is this thing what we call anti-differentiation. Actually, when we use the prefix anti, it's something against, or another term that we can connect it to is something that is the opposite. So when we do the opposite of differentiation, that is what we call integration. Just like addition has the opposite, which is subtraction, and vice versa. Subtraction has the opposite, which is addition. Now, in terms of calculus, the opposite of differentiation is integration. Or shall we say, the opposite of integration is differentiation. So being the opposite of differentiation, we call it anti-differentiation. So let's say, for example, if the function of x is equal to x cubed, we've learned from your differential calculus that its derivative, specifically its first derivative, is 3x squared, right? Another expression here, we add 1 to the original x cubed plus 1, its derivative is still 3x squared because this one is a constant, right? So its derivative is 0. And we say that if it's, say for example, instead of adding 1, we subtract 1 from the function from x cubed in a given original function of x, the derivative is still 3x squared. So there is this statement that says if the function of x is equal to x cubed plus 3, it is this particular function that we call the antiderivative of 3x squared. Being the derivative of the function, then the antiderivative is the function which was differentiated. I hope you get me clearly there. The answer of differentiation, so this is 3x squared for all these different functions of x, is said to have the antiderivative, which is x cubed plus c. So meaning whatever is this c, as long as of course it represents a constant, when differentiated, its answer would still be 3x squared. So we say that the antiderivative of 3x squared is x cubed plus c. Later on, you will know that when we take the integral of this 3x squared, our answer is x cubed plus c. That is why I've said when we speak of antiderivative, it's just like finding for the integral or processing the given function in terms of integration. Okay? Now, you can have a of x here, which is 3x squared, and it's still equal to x cubed plus c. Another way of presenting what we call the antiderivative. So this expression here, you can find this in other textbooks, not in standard books. This would mean that the 3x squared is the antiderivative of this particular expression, x cubed plus c. So antidifferentiation is the process of finding the antiderivative. Or shall I say, as I've said already, we call it the process of integration. Okay? Now we go to the indefinite integral. So last meeting, I gave you the orientation of the course and gave you an idea that in the application part of the course, we will have already answers which are real quantities. So meaning your answers will not be any more functions of x or y or any variable for that matter. Why? Because you're already given what we call a definite integral. An integral which has what we call limits. Now, for now, since we're starting the course, you will be introduced to what we call as the indefinite integral. Indefinite in the sense that its value is not defined yet because there are no set limits to it. So we did not put any limit yet in the process of our integration. So as such, we call it an indefinite integral. So in the case of the indefinite integral, since it doesn't have the limit class, it will always have a plus c after you're done evaluating the given integral. It will always have what we call as the arbitrary constant of integration. So whenever a function of x is integrated, you will also have a function of x as an answer. So a function of y will also yield a function of y as an answer. Function of v will also yield a function of v as the answer. Plus, don't forget the arbitrary constant of integration. So if you missed writing the plus c, you will have deduction because this plus c can only be omitted or forgotten when we're dealing with the definite integral. That is the integral with the limits already. So you can see here that this is our integral sign. Write it like that. This expression or the expression that follows the integral sign is the integrand, and this is the variable of integration. So the differential of x tells you, this dx here, tells you that you are to integrate this given integrand in terms of x. Okay, you will integrate it in terms of x. Now let's look into the note. The integral sign, this one, evolved from the Greek letter summation. So actually it came from the summation symbol. You will know also later why this Greek letter summation was changed to this when we go to the application part. Now the dx is an appendage associated with the delta x, or meaning something representing a change. So delta x is now written as dx. The integrand should be of the same variable as the appendage. So meaning there is no way that this is, for example, this is y, and here your differential is in terms of x. If that is the case, you cannot integrate your given expression. Okay? So now it's very clear here that integration and anti-differentiation are two the same things. They are just, this one is just one long word compared to integration. But when you find the antiderivative of a given function, it's just like integrating it. Okay? It's just like you also perform the process of integration. As you could see here, you have the integral of 3x squared dx is equal to x cubed plus c. How did this came about? We will know in the succeeding slides. Any question? Okay, so no question. So we go to the simple power formula. Okay, what's the simple power formula? From the term power formula, then your function or your variable is raised to an exponent. Now, the key to finding the integral of any function or group of functions for a given integral to be processed is sometimes starting with the power formula. So if it cannot be really processed purely by the use of the power formula, that's the time. So I always say to my student, that's the time that you will have to think if there are still other formulas that are applicable to your given function. If not, then we go a little bit higher into finding the techniques that will first simplify the given function, and then once simplified, process it or find its integral using the formulas that I will be discussing one by one here now. So if you will find the integral of kx, where k is any function, that would be kx plus c. What happened here, I'll just enlarge. What happened here is just you drop the, sorry for that, you drop this d, you took it out, and you just copy the k and then the x. What is this k? This k has to be a constant. So whenever you're integrating a constant, so what's a constant? Any real quantity or any arbitrary quantity. So it could be letters A, B, C, D. Okay, as long as it's a constant, it's not a variable. The integral of a constant is the constant itself times x, because the integral of dx is equal to x plus c. You simply drop the d. Okay? The integral of the differential of x is x. So as such, you see this first formula. Whenever your particular constant k is multiplied to a function, let me change, let me clear. Multiplied to a particular function here, f of x, what you do, you set aside the constant. It's just like you write this in the, you write this particular equation, integral equation in this form, k times the integral of the function of x dx. Why? Because this one is a constant, or it's a factorable constant. So you can place it before the integral and simply get the integral of this given function. So if you integrate a given function of x, the answer is also a function of x, but not the original function. It's also a function in terms of x, but is not the same as the given function of x. This is what it meant here. But not that you will misunderstood this one, that whatever you have in here, it's the same thing in here that you see on the right side. So as an example, we can have, let's say, integral of 12 x dx. You can write this as 12 integral of x dx. You set aside the constant and you just process the integral of the expression having the variable. Now, the third one simply tells you that, just like what you do it here in differentiation, I'm concentrating here on integration. When you have several terms to be integrated, what you do, you integrate it piece by piece. Like in this case, you have two terms here to be integrated. What you do, you integrate the first term and add to it the integral of the second term. So you process it piece by piece, just like what you do in differentiation. Isn't it that you also differentiate it piece by piece if you have several terms in your function? So that same applies to integration. Integrate it piece by piece. Now comes the fourth formula, which is actually the most basic and let's say the most basic of all formulas, fundamental in nature, is this one, the power rule. Let me just, okay, reduce the size of the slide. So x raised to n dx, where n is any real number, is equal to x raised to n plus 1 divided by n plus 1 plus c. What happens here is you copy your variable or you copy your function, raise it to an exponent which is 1, wherein you have added 1 to it. So this could be 10, this could be 12, this could be 0.5. So you add 1 to it. And then what is the denominator for such an expression is the same as your function itself. So if this is n plus 1, this is also n plus 1. And then you add the arbitrary constant of integration. Notice, class, this is very important that in this case, you cannot have n equal to -1 because it will be a different formula. You'll be given a different formula to use if your n, the exponent of your function, is -1. So you can use it for any n as long as it's not -1. So as an example, you have here, example 1 using this one, number 2, and the power rule. So you set aside the 3 and you integrate the x. So you will have x raised to 1 plus 1. This is understood to be 1. And you have in the denominator 1 plus 1. And you have 3 halves x squared. So 3 over 2. Then you have x squared plus c. This is said to be the antiderivative of 3x. This is said to be the integral of 3x dx. Okay, in this particular example, you made use of 2 and 4. Any question? Okay, so if there's none, we'll continue. So we'll just have this reduced, that way you can see everything. Okay, so example 2, you have -2 t squared dt. Okay, set aside -2, then process t squared. That would be t cubed over 3. And then you have the -2 in here, plus c. In the case of the third example, there's a need for you to use expansion first and number 3 in here. So you need to have it expanded first. So you have here x squared plus 3 quantity squared. So it was expanded to x to the 4th plus 6x squared plus 9. Okay? Then you now process it piece by piece. So integral of x to the 4th, integral of 6x squared, which requires that 6 should be written before the integral, and then you have 9. Okay? When you use power rule for x to the 4th, that would be x to the 5th over 5. When you use power rule for x squared, that would be x cubed over 3. So you add 1 here over 3. But since you have a 6 here, 6 over 3 is 2. So 2x cubed. Now this one is what I'm telling you a while ago. The integral of dx is you simply drop the d. So that would be x multiplied to 9. So we say this is the antiderivative of the quantity x squared plus d squared. Okay, or it's the integral. Now, number 4, you have 1 over x cubed. So the initial thing that you have to do is convert this rational expression into something wherein you can use the power rule without having to worry about the denominator. So your 1 over x cubed is x raised to -3. When you use power rule, this would become x raised to -2 over -2. So you can see here. And since this is -2, you place it in the denominator. So -1/2 x squared plus c. So there's a note here. The power rule is also applicable to fractional and negative exponents. Just like what you have here. You have a negative exponent, and this can be even 1 over square root of x, wherein it's negative at the same time a fraction exponent. Because we know if it's square root, it's equivalent to an exponent which is 1/2. Okay? So power rule is applicable to fractional and negative exponents as well. Any questions? Okay. So if there aren't any questions, I hope you're still there. So let's go to the simple trigonometric functions and their corresponding integrals. So what you have here on the first columns are the derivatives of this function. The derivatives of this function, when integrated, will give you the given function. So meaning these derivatives, when you integrate, it will give you the original functions here on the left, which you differentiated. Example, the cosine of u is sine u. The integral of sine u is negative cosine u. The integral of secant squared is tangent u. The integral of cosecant squared u is negative cotangent u. The integral of, yes. The integral of secant u tangent u is secant u, and the integral of cosecant u cotangent u is negative cosecant u. So you can see very clearly here that integration is an opposite of differentiation. Now, I'd like you to look into the formulas and ask me questions if you have any. Any question? Okay, so there are no questions. We will proceed. Now, example 1, we'll substitute, or rather not substitute, but we will apply. We will apply the formulas that we have learned in the previous slide to the following examples. So, cosecant x, 3 cosecant x minus 2 sine x. What's the integral of the cosine? It's the sine. What's the integral of the sine? It's the negative cosine. So this becomes positive. Okay, so you just apply it. So you apply the formula at the same time, apply the first 4 concepts that were introduced in the process of integration. So you have to process this piece by piece since you have 2 terms. Now, in the case of 1 over sine x squared, you have to square first the original expression. So 1 over sine squared x is cosecant squared x. The reciprocal of sine squared is cosecant squared x. This you have learned in your trigonometry. What's the integral of the cosecant squared x? It's negative cotangent x plus c. How do you know that this answer of yours is correct? Differentiate this one. Your answer, if you differentiate this, it should give you the original integral because one is the opposite or the reverse of another. Okay? So integral of cosecant squared x dx is negative cotangent x. Now we attach the plus c because, as I've said, we're dealing with an indefinite integral. As for the tangent squared, do we have the direct formula for the tangent squared? We don't. You look here. We don't have the integral of the tangent squared. So that's the time that you will think of identities. Identities that will write tangent x squared to its equivalent. That way it can be integrated. Now in senior high, you learned that secant squared x minus 1 is tangent squared x. Right? Secant squared or 1 plus tangent squared x is equal to secant squared x. So we just replace your tangent squared x here by secant squared x minus 1. After that, you evaluate your given integral piece by piece. So the integral of the secant squared x is tangent x, and the integral of dx is x. You drop the d. Copy the sign and then plus C. Questions? None? Okay. Now we proceed. What about number 4? You have 3 cosine cube x minus 4 sine cube x over sine squared cosine squared x. Okay, so this is where your trigonometric identities will really be very useful. Now, what will happen here? What you do? This sine squared, cosine squared, you distribute to each of these terms here in the numerator. So what happened is you have cosecant squared. Now, I will get, wait, class. I'll go to the Jamboard and show to you how it's done. Okay? That way, you will learn the step-by-step processing. So let me share the Jamboard so we can write something there. Okay. So the first thing that you saw there, just change to black. Integral of 3 cosine cube x minus 4 sine of cube x divided by sine squared x cosine squared x dx. If you will use this as a divisor for each of the terms that you have in the numerator, this is how it will be. 3, it's a constant, so I place it before my integral. Then I will have cosine squared x over sine squared x for this one. And I will have cosine x over cosine squared x. You understand? I split these two and I split these two as well, so that you will understand why the solution in the slide is the way it is. Now, in the second integral, if you will combine, by the way, these two, not combine, but multiply, you will still have the original here. You'll have 4 integral of, you will have sine squared x all over sine squared x for this. And I will have here sine x, because it's sine cube, over cosine squared x dx. Oh, sorry. We have this, and it should have a dx, and this one. Okay? Before I proceed, do you follow what I'm doing? If you cannot understand, let me know. But do you understand? Can you follow? If you don't have your microphone on, you can place your answer on the chat box. If you have questions as well, you can place it on the chat box. Do you understand what I'm doing here? So no reaction in the chat box? No reaction in the chat box. What about, you have any questions? Are you still there? Danielle Ong, are you still there? Mr. Gembal, are you still there?
Yes, miss.
Okay. Probably I was just my mic is not working. Oh, it's okay. Then please do react using the chat box, okay? Or answer using your chat box. So I will have here 3. What's cosine squared over sine squared? What's cosine squared over sine squared? Can you place it on the chat box? Thank you. Thank you. I thought I'm alone here. Wait, class. So it's cotangent squared x. This cosine cancels with this cosine. That gives us only 1 over cosine. What is 1 over cosine? 1 over cosine is second x, correct. So I'll place here second x dx. Now the second, we have 4 integral of, this is 1, right? Now you have sine x over cosine x. I'll write it in this form, class, so you would see. I'll write here cosine squared x, but it's negative. Cosine of x raised to negative 2. Or I will place it like this so you will not be confused. So I'll write it as cosine x raised to negative 2 for this one. Negative because it's in the denominator times the sine of x dx. Okay? Now, how will you process this one? Cotangent squared x and you have second of x. How is it? How will you process this one? Cosine, sine squared is cotangent squared and you have second here. Is it cosine squared? Correct. So you have second x here. What will you do with this expression? That way, you can get the integral using the set of formulas that I have provided for you. What will you do with this one? That way, you can use the set of formulas that were provided for you. Okay, so there is one here in the chat box. Okay, probably not associated with my question. So what will you do now to cotangent squared x times second of x? That way, you will be able to integrate it. Anybody? Anyone? How will this be integrated based on the formula that was provided for you? Remember, class, the formula that was provided for you is just sine, cosine, cotangent squared, second squared, and second cotangent, second tangent, and cotangent cosecant. How will you process this first integral? Anybody? I'm sure you have your introduction in integral calculus in senior high. How will this be processed? Or, second, here. This one may be easier. How will you process the second integral? Whichever of the two integrals you will know how to process, let me know. But stick to the point wherein you will just use the identities and the formulas that were provided to you. Let me show to you again the formulas. But before that, I've changed my mind because you will see the answer in the PowerPoint presentation. So let me check. How will you process these two integrals here using only the basic formulas of integration? Wala gid. Kasugod pa lang ta. Wala pa ta gani sa tunga-tunga nga ato to ang parte ka record ni integral. How will you process? Any integral here which you know how to process, let me know. Which of the two or which of the two you have the answers, let me know. I give you 2 minutes to do that. Think of how will you integrate these two using only, take note, identities and the formulas that were shown to you a while ago. Lagi class. Wala gid. Or if you think you have a different take on this one, different manner of solving, can you share it? Or miss, it would be better if you do it like this. Or miss, it would be better if instead of writing this particular identity, I'd rather cancel this and this, so I will have something like this. Something like that. Any suggestion? Hmm? Why kid? Why did siya class? Okay. Use Pythagorean identity sa cotangent squared. Thank you for that, Beatrice, but I don't think we can use it in here, and that will complicate things for us. We try to take things simple by simply thinking of using identities and using the formulas that were shown to you a while ago. What do you think would be the best take on this? Hmm? Okay. We already used like more than 5 minutes for this. Instead of presenting your cosine squared x here and sine squared x in here as cotangent squared, there's nothing wrong with this. And the remaining cosine here is grouped together with the cosine squared in here in the denominator. There's nothing wrong also with doing it like this because you still have the original fraction. If you distributed sine squared x and cosine squared x to 3 cosine cube x. There's nothing wrong with that. But the thing is, class, I intentionally write it this way for you to see that if you stick to this given set of trigonometric functions, it would be like, for now, impossible for you without transformation to process the given integral. Why am I saying it's difficult? Because there is no association between cotangent squared and second x. Probably we have an association between cotangent squared x and cosecant, but not with second. So a different way of looking into this is like this, okay? I'll erase what I have written here. Okay, and then cancel this cosine squared here with this cosine squared here. I think we did not violate any rule with that. And then I write this second squared here by the way I have written the cosine squared here. So -2, and I'll multiply it with this cosine of x. So meaning, this cosine of x here should not be cancelled. Do you get it? Now, I'm giving you already the hint. They look similar, right? They look similar. How will they be integrated now? Using power rule. Take note, how will they be now integrated? Using power rule. So what is power rule? So I'll write here power rule so you will have a guide. Power rule tells you that the integral of u raised to n du is equal to u raised to n plus 1, excuse me class, over n plus 1 plus c. You have to understand that power rule is only applicable to this formula when the derivative of the u, whatever is that u, is with it. So meaning, if this u is x, the derivative of that is dx. That is why we're able to use x raised to n plus 1 over n plus 1 plus c as the answer. If this u is not x, it could be any function, we can still use power rule or power formula by making sure that together with this u raised to n, you have the derivative of your u. Like if this is cosine, this should be negative sine. If this is sine, this should be cosine, something like that. So then, if you will use power rule for the integral that I have shown to you here on top, what then should be our answer? I will use u raised to n du, the power formula, in processing this simplified expression for the original one. What will you do? I will not anymore write the integral because this can be processed already using the one that I have written below. So what will you do? The answer is 3. Isn't it that your u here is sine x? This is your u. What's the du of sine x? Isn't it cosine x dx? So this is your u, this is your du, and this is your n. Are you getting me? Then what is the answer based on power rule? That would be u raised to n plus 1. What is your u? Isn't it that the u is sine x, the du is cosine x dx? Ari na siya, complete na siya. Then you can use power rule. So your u, which is sine x, will be raised to n plus 1. Your n is negative 2 plus 1, that would be negative 1. All over, isn't this one? So over negative 1. That's for this. That's the answer for that. For this one, this is your u. Your u is cosine of x. What's the du? It's negative sine x dx. So you take this negative sign here, replace it by a positive sign, and place it in here. So you place negative sine x dx. That way, you can use now the formula for power rule. So this will be now plus, because you use the negative sign here to complete the derivative of the cosine. And your u is cosine of x. It's negative 2 plus 1. It's also negative 1, just like the first term here, divided by negative 1. You have your constant 4 here, so it should be present still in here. Plus C. How will you simplify this answer? Isn't the negative 1 here, exponent tells you that this is 1 over sine, and this is 1 over cosine? Right? So your answer should be, so your final answer should be, I'll place it here on top, negative, because negative here, negative 3. What's the opposite of, or what's the equivalent of 1 over sine x? That is cosecant x. And what's the equivalent of, so this is minus 4. So what's the equivalent of 1 over cosine x? That's secant of x plus c. So this is the answer to this particular integral using simple identities, using mathematical manipulation and critical thinking skills. Do you have any questions? No questions? Okay, then I will go back to our PowerPoint. We go to, so make sure you, so wait, this is our answer. So you check whether this is the answer that is written in the PowerPoint. You share. Oh, I can't find the PowerPoint. Where's the PowerPoint? My class. Okay, so here's the answer. Okay. Now, what about this one? You have 1 over 1 minus cosine of x dx. There is no direct formula that will lead you to the integral of this. Okay, wait, ha? Run out sa ilan ni Javier. Noted, it's noted. So there is no direct integral. There's no direct answer to this integral, by the way, based on our formula. So wala. So what you should do first, you have to use manipulation. And what is that manipulation? So take note, class, listen to this because this is very important. Whenever you're given a rational expression that contains trigonometric functions in that denominator, together with a constant, what you will do, you multiply your given expression by the conjugate of your denominator. So question, Miss Ali, what is a conjugate? A conjugate is an expression in which you have exact terms present in your function, but instead of having negative in here, you will have positive. And since you don't want to alter the original integral, you will multiply both the numerator and the denominator by that conjugate expression. So that's what we've done here. We multiplied 1 over 1 minus cosine x by the denominator of 1 minus cosine x. So both the numerator and the denominator. The question is, have we violated any mathematical rule in doing this? The answer is no, because 1 plus cosine x over 1 plus cosine x is just 1. So meaning you still have the original given expression intact. You did not change it at all. Now, in the process, since you already multiplied both the numerator and the denominator by the conjugate of your denominator, you process your expression using algebra. So your numerator, of course, will be this, and your denominator will be this. But what is this? What is 1 minus cosine squared x? Using your trigonometry in high school, cosine squared x plus sine squared x is equal to 1. And as such, 1 minus cosine squared x is sine squared x. So what's done here is we change it to this one. And since we have two terms in our numerator, we process the integral piece by piece and use the sine squared of x as the denominator. So you have 1 over sine squared x, and you will have cosine over sine x, and another 1 over sine x here. Okay? What is sine squared x? What is 1 over sine squared x? It's cosecant squared x. And this cosine x over sine x is cotangent x. And this 1 over sine x is cosecant x. Why manipulate it in this form, Miss Ali? Because these integrals now can use the formulas that were provided to you. The integral of the cosecant squared x is the negative cotangent x, and the integral of the cotangent x cosecant x is negative cosecant x dx. Or rather, cosecant x plus c, not dx, because we have here the dx in the integral. Okay, so this is the answer, class. So if you're given something like this, before it can arrive to this answer, it has to go through this process. How you learn that you will use this particular techniques? For this one, it's really the technique that is being used. But how you learn later after doing it like this, that you will do it like this, you learn it by discovery. When you practice processing integrals already. Do you get it? So the answer to cosecant squared to rather 1 over 1 minus cosine x dx is negative cotangent x minus cosecant x plus c. Questions? So far, as a review, we've discussed the application of these integration formulas together with previous knowledge on identities. Okay? And of course, mathematical manipulation in the case of this one. Now, any question? Okay, I'll stop sharing. Okay, we will continue on trigonometric functions still. So we are on slide 11 of 19. What you have here on slide 11 is actually the common trigonometric functions and the common identities. So I'm not sure if you'll be able to see it here, if projected. So what you'll do, I placed this already. I placed this slide already in Canvas. There's a reference here as to where you can access this particular file or images. So you can access it on the indicated, website. Okay. Can you see, by the way, the projected slide? Still not?
Makita namin.
Makita nyo na. Nag-bisyo sa kaina. So this is the set of identities that I'm sure you haven't totally forgotten yet. So some might be something that is new to some, but I think others know already some of this. Okay? So please study on this. Anyway, you can access this file in Canvas already. Now we'll proceed. Let me know if you can, if the slide is not showing. Now we go to, aside from those formulas that you have learned regarding integration, specifically on the last topic on the use of the integration formulas, we now go to substitution. It's possible that in some integrals, there's a need for you to represent a particular group of functions or a function and a derivative into one particular variable. That way, you will see the remaining function and the corresponding derivative of that remaining function. So in that case, you're using what we call substitution. So if, for example, if you set u as your given function of x, then we say, yes, John Mark, not yet seen.
Wala na miss, miss, nag-silo sa substitution.
Thank you, thank you. Okay, so there you go, substitution. So if u is equal to g of x, then we say du is equal to g prime of x dx. You get the derivative of the left side. So that's du. And the derivative of the right side, g of x is a general representation. So if you want to get its derivative, that's g prime of x dx. And if you're going to apply it in this scenario, the function of u du will be now, or rather specifically the integral of the function of u du will now be the integral of the function of g of x, because we set u as g of x, and the du will be g prime of x dx. In that case, this is actually already applied to the previous example I've shown to you. Since the derivative of your g of x is already multiplied to it, in the case of the use of the power rule I've shown to you in the last example, then you can use the correct formula for this g of x, the f of g of x that we have. In our case, it's the power rule that we use. So since the derivative of your function is already together with it or is multiplied to it, then you can now write the integral for that particular function. In the case of the last example, the integral of that particular function is using the power formula. So that would be generally represented here by capital F of u plus c, where f of u is equivalent to f of g of x plus c. So there are two ways here that you should remember this particular substitution equation, or two ways that will make it easily remembered. You have to recognize the u du and the u raised to n du pattern, just like the one I have shown to you in the last example. It's possible to use the power rule as long as the derivative of the selected u is together with it or is multiplied to it, just like in the case in here, u raised to n du. Then I can now use power rule for u raised to n. Now, it's also recommended or suggested that if there's a need for you to complete the derivative of your u by multiplying it with a constant or dividing it by a constant, you may do so. So as long as the original integral will be multiplied by 1. So let's say, for example, you need 1/2 in your du. So you need to multiply the original integral by 2 over 2. That way, you can make use of the 1/2 together with the du. That way, your derivative now will be complete, and the 2 in the numerator of your 1/2 should be placed before the integral. It's always suggested that you multiply your integral by an expression equal to 1. So if you need only a constant in the derivative of your u, you may introduce that constant, that makes sure that before the integral, there's the reciprocal of that particular constant. That way, it's as if you have only multiplied your integral by 1. I think you will understand it better with an example. Let me see. Okay, let me see if I have placed it in here. Here, 15x cubed plus 1 times 5x cubed plus 1 times 15x squared dx. This is really one given integral. What others would do is distribute. So I will annotate here. So the most common thing that should be done here by the students is distribute 15x cubed. So this could be processed like 15 times 5, that's 75x, right? 75x to the 5th plus 15x squared, right? And What's happened to my pen? What's happening to my pen? Dx, right? You distribute. So you will have this. Then you use power rule. Okay, so if this is 75x to the fifth, then if you use power rule, that would be 75 x raised to 6 over 6 plus 15 x cubed over 3 plus c. Right? That's a simple power rule. But if you wish to use substitution, that way you won't have to deal with big quantities here. Let me just first clear. You can use substitution. Let u equal to 5x cubed plus 1. This entire thing. And du is 15x squared. Dx. So you could see that you have the 15x squared dx already. So then what you're going to do, you will just simply treat the whole quantity 5x cubed plus 1 to be raised to 1. That way you use power rule. So if you use power rule to this u, you will be having an answer 5x cubed plus 1, quantity raised to 2, 1 plus 1 over 2, plus c. Isn't this isn't this more easy, rather easier than the one wherein you are to distribute? Or the others will, probably there will be some or a lot that will be disagreeing with me, but I find this easier compared to having to distribute. Okay? But there's nothing wrong with distributing and using power rule. But that's only okay, class, if you can use power rule in the resulting expression. What if power rule cannot be used anymore? Pure power rule. Then you will really have to resort to substitution the way it's presented in here. Okay? Any question to number 1? Okay, none. So we go to number 2. This time you have this integral. Okay, we'll not read it anymore. If you set your u to be x squared plus 6x, it's just like this square root, and being in the denominator tells you that your exponent here is negative 1/2. Okay? What is the derivative of this x squared plus 6x? It's 2x plus 6, right? Derivative of x squared is 2x. Derivative of 6x is 6. Isn't it the one that you're seeing here? This is now 2x plus 6. So recognizing that when you set this as your u, with n equal to negative 1/2, you have this du here, which is 2 times the quantity x plus 3 equal to 2x plus 6, which is the derivative of your u here, allows you to use power rule. So when you use power rule here, plus 1 here makes it 1/2 over 1/2. So since this is already positive, then x squared plus 6x will be placed under the radical sign, and this 1/2 goes up in the numerator, plus 6. So without substitution, class, you will have a hard time integrating this one, knowing that there's no direct association upon inspection between the denominator and the numerator. So you have to really use substitution in here, coupled with power formula. Any questions? Okay, we go to the next. Here, example 3. 10 sine 10x dx. If you let 10x as your u, your du is 10 dx, right? Derivative of this 10x is 10 dx. So if you use the formula sine u, which is negative cosine u plus c in its integral, the du of the u in the sign is present here already in the form of 10 dx. So meaning, class, we annotate. meaning this 10 should be transferred here. If it's written, it would look something like this, sine of 10x times 10 dx. This is comparable to sine u du. This is your du. This is sine u. So what's the integral? That's what's rather the integral of sine u. As per formula, the integral of sine u is negative cosine u. And what is u? That's 10x. So it's negative cosine of 10x plus c. So you have substituted u for the 10x and integrated the expression sine using the formula for the integral of the sine. And that would be yielding the cosine. This same is true with this. This cotangent x could be your u, and the negative 3 could be your n. What's the du? U is cotangent x. What's the du? It's negative cosecant squared x dx. The derivative of cotangent is negative cosecant squared x dx. Here. So it's already in here in the numerator. So this could be written as or interpreted as cotangent of x raised to negative 3 times negative cosecant squared x dx. This is your u, this is your n, and this is your du. So you process this integral now using power rule because you have an expression u raised to n. So now it's negative 3 plus 1, it's negative 2 over negative 2. So since this is negative, you have to write it in the denominator. What is the u? Cotangent x squared x. This squared came from the negative 2 in here, which you place here in the denominator. The 2 is in here. The negative sign is in here. So what is 1 over cotangent squared? It's tangent squared. So this one is identity already. The equivalent of 1 over cotangent squared x is tangent squared x dx. Okay? Any questions? Okay, we go to the next. Okay, we'll clear the markings here. What about this one? I think this is similar to the first example. X squared, x cubed minus 1 raised to 4 dx. Actually, class, whenever you see this expression, whenever the variable outside is of order or degree less than 1, the variable inside, you can check whether this could be the derivative of this one. So if you substituted u for x cubed minus 1, this entire thing, with n being equal to 4, the derivative of your u is 3x squared dx. What you only have is x squared dx. So this is simplified or to be dealt with the way it was suggested in the slide where substitution was presented. You introduce 3 here because you need 3x squared dx and you place 1/3 outside the integral. Placing 3 here and dividing it by 3 here, it's just equivalent to multiplying it by 1. So it's just like you have multiplied this original integral by 1. The purpose of placing 3 here is for your derivative to be complete because it's 3x squared dx. You only have x squared dx. So you place 3 and then outside your integral, you place 1/3. So the process is you have done multiplication by 3 over 3. So now you have 1/3 integral of x cubed minus 1, quantity raised to 4, 3x squared dx. This is the u, this is the n, This is the du. So if you're going to use power rule, this will be 5 u raised to 5 over 5. This is your 1/3 here plus c. What is the u? The u is x cubed minus 1. So you place it here. X cubed minus 1 raised to 5. This 5 and this 3 will be multiplied to give a 15. And this is your answer. Okay? Question? Okay. We go to the next if there aren't any questions. So next on substitution. Last 3 slides. Yes, this is the third to the last. This one is really very, very useful. Useful. Why? This 1 plus x squared, cube root of 1 plus x squared, this could be presented as 1 plus x squared raised to 1/3. Okay, cube root. And you have here 5x. If you set u as 1 plus x squared, this one, the derivative of that is 2x dx. You already have the x dx here. You simply have to set aside the 5 and introduce a 2 in here. So what you do, since you need the 2 in here, you multiply by 2 over 2. The 1/2 goes together with the 5, so this becomes 5/2, and the 2 goes together with the x here and the dx here. That way, you will have an expression which is u raised to n du. Now, if this 1/3, you add 1 to it, that would be 4/3. Using power rule, your denominator will be 4/3. This 4 and this 2 will multiply, so that would be 8. This 3 and 5 will be multiplied, that would be 15. That's what you see here, 15 over 8. Because this 3 goes up, okay? Your u is 1 plus x squared, and it will be raised to an exponent 4 over 3 plus c. So you see how very important substitution is? Because without substitution, class, you won't be able to process this one using any formula. It cannot be processed. Okay? Second to the last. 7. 5x cubed plus 3x minus 8. Check. I have x cubed here and I have x here. If this is differentiated, this will be x squared and this will be none. I see here an x squared, right? So let's check whether it's possible that this 5x squared plus 1 could be the derivative of this expression. So u is 5x cubed plus 3x minus 8. Du is 15x squared plus 3 dx. 15x squared plus 3 dx. You only have 5x squared plus 1. If you will multiply this entire expression by 3, that would be 15x squared plus 3. That derivative that you need to go with the u. That way you can use power rule. So you need to introduce 3 here. That requires you to multiply the original integral by 3 over 3. The 1/3 should be written before your integral, and you process the square root of 5x cubed plus 3x minus 8 using power rule. So if this square root tells you that the exponent is 1/2, you add 1 to it, that would be 3/2. And of course, it will be divided by 3/2 here. The 2 in the 3/2 goes up, so that would be 2 over 9. And your u, which is 5x cubed plus 3x minus 8, will now be raised to 3/2. And don't forget the very important c. So by substitution, we have set this as the u, this as the n, which is 1/2, and this is your, I place a dot here, meaning this is multiplication. This is your entire du. So don't get accustomed, class, or don't get used to the fact na ang DU isa lang na permica term. No, it could be 2 terms, it could even be 3 terms. As long as it will correctly represent the derivative of the U, which you have set. Okay, before I go to the last slide, any question? Any question? Okay, then let me clear the markings here and go to the last slide. Okay, last example, example 8. This deals with the sine and the cosine. Similar to our example in under trigonometric formulas. So sine 3x, cosine cube 3x. When you look at it, class, when I was a student, I would right away say there is a connection between this cosine 3x and the sine 3x. Because the derivative of my cosine is negative sine. Okay? So one way of doing it is in the presentation that you have here, or it could be the one that I have mentioned a while ago. So if you process it like this, your sine 3x over cosine 3x, and you have 1 over cosine squared 3x here, it's the same as this one. Okay? This is just manipulation. This one is this. The sine over cosine is tangent. And 1 over cosine is second. Now this being squared, so this is second squared 3x. This tangent is tangent 3x. Now, tangent 3x has that derivative, second squared 3x. But, using chain rule, it should have a 3. Because the derivative of the 3 here in the 3x should be present. So, since you need the 3 here, you need to multiply by 3 over 3. So, you have 1/3 tangent 3x, 3 second squared 3x dx. This is your u. This is your du. So, this u is understood to be raised to 1. So, when you use power rule, that would be u squared over 2. So, it's 1/6. 1 over 3 times 1 over 2 is 1/6 tangent squared 3x plus c. Another way of doing this is very simple. So this could be an answer. Another way of doing this is you have cosine of 3x raised to negative 3, this one, times the sine of 3x dx. If I will use power rule, in this case, if I use power rule, this is my u and this is my n. So this should be du. What's the derivative of the cosine 3x? It's negative sine 3x times 3. So what do I lack? I introduce a negative 3 here, so I should place here negative 1/3. Okay? You get it? Para makagamit ko power rule here. So if I use power rule here, if I use power rule there, because u raised to n du can allow me to use power rule for this one, then my answer will be negative 1/3 cosine of 3x times negative 2 over negative 2 plus c. Equivalent to 1/6 1 over cosine squared 3x plus c. What's cosine squared 3x? It's 1/6 second squared 3x plus c. You can have this as your answer. You can have this as your answer. Both using substitution. Do you get it? Do you have any questions, class? Any questions? There's none. This is the end of module 1. Okay, I will stop sharing here. We have processed the entire module 1. I'd like to share to you what we have in Canvas so you will see class, ha? Wait lang. Okay, allow me to share my screen.